Right. So, let us now today look at the general correspondence between a stochastic differential equation for a diffusion process and the corresponding Fokker-Planck equation. So, let us call this the general stochastic differential equation and the Fokker-Planck equation correspondence. Just to refresh your memories, let us go back and look at what we had come out with in the case of the ordinary Langevin equation. There we had V dot, a velocity, one component was minus gamma V plus a noise. This noise, after I divided by m, etc., etc., this turned out to be square root of 2 gamma kt over m, and then there was a zeta of t here. I have used the fluctuation dissipation theorem divided by m and so on, and then you had a 2m gamma kt divided by m squared. I put it inside the square root, so this becomes an m, and this implied, if you recall, the original Fokker-Planck equation for the Ornstein-Uhlenbeck distribution. So, this implied immediately that the conditional density of V satisfied this equation, P of Vt divided by T is equal to gamma times delta over delta V, V times P, plus gamma kt over m, this was k Boltzmann T over m d2p over dv2, and we had to solve this with some specific initial condition v naught, for instance. So, the initial condition was p of v comma 0 equal to a delta function at v naught, and this led to p of vt equal to the Ornstein-Uhlenbeck distribution. That was the first Fokker-Planck equation we came out with, right. We also saw what happened if you assume the velocity to be a delta correlated process. Then we were in the diffusion regime. So, we saw that for t much greater than gamma inverse, which we could implement by actually going back to this equation and then throwing out the inertia term and retaining just this term here, right, in which case we had a term high friction limit or high friction limit. We had x dot, that is V, is equal to the same thing here, but square root of 2 k Boltzmann T over m gamma zeta of t, because this term was negligible and I took this on this side and brought the gamma down, and you ended up with that thing here, which then implied here, just as this automatically implied it. So, similarly back here you have delta p of x t over delta t equal to k Boltzmann T over m gamma d2p over dx2. This was the ordinary diffusion equation, because this quantity was the diffusion coefficient. So, these are special cases of a more general result which I wrote down, which was that if you have an equation which says x dot plus some matrix x, this was a higher dimensional process, and this is some this quantity is an n by 1 column vector, and the drift was linear in it. This here on the right hand side was equal to some coefficients, constant coefficients, not a function or anything like that, times a noise of some kind. So, there were some coefficients, constant coefficients, and we will make this precise in a minute, and then there was a vector valued noise zeta of t. So, these are all n by 1 quantities, and this is an n by n drift matrix. Okay. So, if you had a situation like this, which is a special case, which is a generalization of this fellow here, right. So, the reason we want that is because we want to be able to write down Fokker-Planck equations for the phase space density, joint density in x as well as v together. So, if you had a situation like this, then this immediately implied that delta over delta t, and whenever there is a phase space density, namely a density in more than one variable, I will use the symbol rho, so that it is distinct from this little p. Okay. So, this quantity delta over delta, this quantity here was equal to Kij delta over delta xi xj rho plus some matrix, constant matrix formed from these coefficients here, and the natural thing to call it is a diffusion matrix Dij d2 rho over dxi dxj. This diffusion matrix, there is a definite prescription for finding it from these coefficients. We are going to write it in the more general case. So, I am not bothered about writing this down in each special case or anything like that. Suffice it to say that just like in these cases, this was a constant, this was a constant, etc. Essentially, it is the square of this constant divided by 2. That is what is, but I want to make it a little more systematic. So, you end up with an equation like this. This is the Fokker-Planck equation, right. Now, we can apply this to the situation which we did earlier, namely the Langevin particle in one dimension, and then we did this quickly for 3 dimensions. So, in one dimension, this was of the form x dot was equal to v. So, x dot minus v equal to 0, and v dot plus gamma v, this thing here, essentially we are writing this equation again, is equal to whatever is there, square root of 2 gamma k t k Boltzmann t over m in this fashion, zeta of t. So, the noise, the vector noise is 0 in the first row, and it is equal to this fellow in the second row. So, the coefficient, the matrix of the column vector of coefficients is just this times this, but you actually need a matrix here. So, in this particular problem, let us write what these things were. K was the matrix 0, minus 1, that is for this thing here. By the way, the identification is x1 equal to x, x2 equal to v. That is the identification which we are making to write this down. Then it is 0, minus 1, and then a 0 here and a gamma here, this gamma. So, it is a linear drift matrix. In fact, it is more than that, it is even simpler than that, it is constants everywhere here and it is zeros along this, which helps. And Dij in this case, let me call that matrix D, whose elements are Dij. I do not want to write D alone here without subscripts, because I have used that for this symbol. I have used that symbol for this quantity and we will stick to that. Okay. This thing here is equal to 0, 0, 0 gamma k Boltzmann t over m. So, that is the equation obeyed by the phase space density, and we have done this already. So, let us write that out and then we are on to new material. So, that immediately implies that the phase space density satisfies delta rho over delta t equal to, now we need to put this in Kij. So, the first term is with a minus sign, as you can see, and then you have a k 1 2, that is the only element which is present here, which is minus 1, and therefore it is delta over delta x of v rho with a minus sign. But v is independent of x, x2 is independent of x1. So, this is equal to minus v delta rho over delta x, this is the first term, and then k21 is anyway 0, k22 delta over delta v times whatever is sitting here, whatever is sitting inside here, which is gamma. Okay. So, the next term is plus gamma delta over delta v times v rho delta over delta x2 rho, and x2 is v. Okay. And then the only term present from the diffusion matrix is the 2 2 term, that is the only term that is non-zero out here. So, it gives us exactly what we had in the original Fokker-Planck equation, gamma k Boltzmann T over m d2 rho over delta v2. This is the equation satisfied by the phase space density rho of v x v and t, and you are supposed to solve this equation with some given initial conditions. So, you are supposed to solve it with the initial conditions rho of x v 0 equal to delta of x minus x naught delta of v minus v naught. It is a little harder to solve than the Fokker-Planck equation for the velocity process alone, which did not have this term. Okay. And then we got the Ornstein-Uhlenbeck distribution. Now, you have to use this term as well and solve it. It is not such a trivial solution, but the solution is a general Gaussian in both x and v, a joint Gaussian in x and v. And that Gaussian has the property that as t tends to infinity, this Gaussian goes to the p equilibrium in V, the Maxwellian distribution, multiplied by the solution of the diffusion equation, which of course vanishes as t tends to infinity strictly everywhere, but we want a leading behavior in the asymptotic regime. This is p of x comma t, and this satisfies delta p over delta t equal to d d2p over dx2. That is the regime in which the velocity has lost its memory. Gamma is t is much greater than gamma inverse. Gamma inverse is called the Smoluchowski time. Okay. The correlation time of the velocity this is gamma inverse is called this so it is a time scale in the problem. There is also a length scale in this problem. There is no potential, there is no general external potential, because if the particle were moving in a potential like a harmonic oscillator potential or something like that, you could get a length scale in the problem. But here there is no length scale at all from the potential, no potential, but there is still a length scale, and what would that be? There is a characteristic time scale in the problem, which is gamma inverse. Well, there is a characteristic velocity in the problem, and therefore there is a speed, and therefore there is a length scale. What is the characteristic speed in this problem? There is one quantity of dimension speed the mean square in equilibrium from this, right. So, this v squared equilibrium is kT, k Boltzmann T over m, square root, sorry. This quantity gives you a speed, characteristic speed, Therefore, there is also a length scale. What would you do? You divide by T inverse, right? So, so this fellow here, you put this in, is a characteristic length scale in this problem. This is LT inverse, this is T inverse, so it is an L. You can compute what it is. You can compute what it is. For the Brownian particles we are talking about, we know what the masses are between 10 to the minus 12 and 10 to the minus 15 kilos. We know what the temperature is, 300 Kelvin, so we know kT. We know what gamma is because gamma is related to the viscosity of a fluid. Take water at room temperature for instance, then gamma is of the order of 10 to the minus 6 minus 7 seconds. Therefore, we know what this quantity is. You can compute what this length scale is. It is indeed very tiny, it is very, very tiny. Okay. All right, but we keep at the back of our minds that there is such a length scale even in the absence of an external potential. Okay. So, having got this far, we would like to know what happens next. What happens if I put the system under an external force, under an applied potential, like the harmonic bound particle? Suppose there is a potential present, x dependent potential. What would happen to these equations? Well, the first thing that would happen is that your Langevin equation would become different. Oh, incidentally, we also saw what the 3-dimensional generalization of this was. We wrote the 3-dimensional generalization. This becomes V dot gradient with respect to R rho. This becomes gradient with respect to V dot, the divergence of V times rho with respect to V here, and then this is the del squared with respect to V. So, that part is over, okay. And in general the solution is some kind of Gaussian, which would asymptotically become something like this. Writing it down in 3 dimensions is very messy, but in 1 dimension one can write the explicit solution down, okay. By the way, one important point in the 3-dimensional case, whatever we wrote here in terms of the drift matrix K and so on is still true, but in that case what would happen is in 3D for example, this matrix K would become 0 minus the identity matrix 0 gamma times the identity matrix, where I is a 3 by 3 identity matrix. So, this is fairly straightforward. This is a 6 by 6 object, and right. So, the generalization is kind of trivial to do this. The reason I am emphasizing this is because we would like to, what did we do in the original Langevin case? We actually solved the equation of motion, the Langevin equation, and then started taking velocity averages and so on. Now, you have a matrix equation to solve, which will involve the exponentiation of this matrix. You will have to find e to the power k, just as we found e to the gamma t, you would have e to the kt. That would be your integrating factor if you like. But e to the kt, this matrix has interesting properties, and therefore you can find immediately the eigenvalues are 0 on gamma. So, you can actually find the exponential quite explicitly and write the rest of the solution down. Okay. All right. So, now let us turn to what happens if when you have a potential. So, it is a Brownian particle in a potential. And again, let us do the 1-dimensional case first. So, you have as before first let us do the phase space distribution, and then we will come back and do the positional distribution. It is a little technically a little easier because you can see what are the approximations involved, because we need to now know what is the diffusion regime, we need to know that first. So, let us look at the phase space problem. X dot equal to V as before, and V dot is minus gamma V, same model as before, but now there is an external potential, some f of x, and I divide it by m. So, it is minus 1 over m V prime of x. This is some potential, in a potential V of x, capital V of x. is that term present, and then the last term is exactly as it was before, plus root 2 gamma k Boltzmann T over m zeta of t. This consistency condition to keep the system in equilibrium is going to remain in any case, no matter what V of x does, it would still remain, because what happens is that the velocity will still thermalize, and there is the external potential acting on the particle, we do not care about it, but the velocity will thermalize, and of course the distributions themselves will become very different. There is no reason why now if I write down the phase space density, why the solution should be a generalized Gaussian, no reason at all. The introduction of this V prime of x makes the equation of motion non-linear. Earlier in all the cases we looked at, the equation of motion was linear in the dynamical variables. There was an external noise, but now that is gone. Unless V of x is either a constant or is either a linear function or a quadratic function. If it is a linear function, this becomes a constant, like gravity for instance. If this thing is a quadratic function, it is like the oscillator problem. But in all other cases, the equation of motions themselves become nonlinear in the dynamical variables, and that will going to make it complicated. Okay. Now what is the way in which we write down the Fokker-Planck equation? We can't do what we did earlier because we have this fellow, which is a nonlinear term, right. So the general correspondence goes like this. We do not care what the dimensionality of our phase space variables is, could be n dimensional in general. So let us write the general Langevin equation, general diffusion process has a stochastic equation which is x dot equal to, on the right hand side, some possibly nonlinear function of the variables, and this is also vector valued. So this guy here, x is an n by 1 column matrix, and this is an n by 1 vector force. There is a force for each of these components, and that is in general a function of all the x's, all the coordinates. We have still not taken the most general case where this could be explicitly time dependent, but I said we are not going to look at those problems at the moment. Plus a g of x, this is multiplicative noise in general, but you look at times the noise, but look at what happened. So this is some zeta of t. In general this is some matrix acting on this column vector, but look at what happened in the earlier case. The equation x dot equal to v did not have any noise on the right hand side, but v dot equal to something or the other had a noise because we wrote an equation for a random force on the particle. So the dimensionality of this noise may be lower than the dimensionality of your phase space variables. So we have to allow for that. So suppose this fellow is a nu by 1 column matrix. So you have n equations for the components of this, but only nu of them have noise on the right hand side. And what is the smallest value that nu can have? 1. If it has 0, then everything is deterministic, we do not even have a stochastic equation. 1 less than equal to nu less than equal to n, because all n of them might have noise, we do not care. Right. Okay. Then what sort of matrix has this got to be? It has got to be an n by nu matrix. It has got to be an n by nu matrix. This on the other hand is an n by 1. This is n by 1, and therefore n by nu and then a nu by 1 gives you an n by 1. That is the most general diffusion process that we can write down. There is an n dimensional dynamic set of dynamical variables, and then there is a new dimensional noise on the other side, and the noise is multiplicative in general, and the value of the noise for each coefficient could depend on all the dynamical variables. You can see this is very general out here. The question is, what is the Fokker-Planck equation corresponding to this, and I am just going to write it down. So this implies, and is implied by a Fokker-Planck equation, which is delta rho over delta t equal to minus delta over delta xi fi times rho. It is like a generalized del dot whatever, so it is a divergence term, and then the next term is plus d2 over dxi dxj dij times rho. There is a diffusion matrix, but it is not a set of constant coefficients because you have this sitting here. So the question is, what is this dij equal to? So it is clear that we have to be a little careful. It is not just g squared as it would have been in the one dimensional case. This matrix D is 1/2 G matrix G transpose matrix, because this is n by nu and that follows nu by n. So the product is n by n. D is an n by n diffusion matrix because the indices I and j run from 1 to n, and there is a summation over repeated indices. So in explicit form this implies that dij equal to 1/2 a summation from alpha equal to 1 to nu g I alpha g j alpha. That is what is meant by transpose here, it is clear. So this is the general Langevin equation, the general stochastic differential equation, and this is the general Fokker-Planck. Notice that this set of coefficients is not necessarily constants because it depends on this function g inside here, and it gets differentiated, it is inside. So this is fairly complicated here. Likewise, no matter how nonlinear the force is, this drift term is, it is inside here. So given that, let us try and ask what does our equation look like here for this situation in the one dimensional case. So we want an equation for delta rho over delta t, where this rho is rho of x, v and t. So this is equal to, well, x1 is x and x2 is v. So we want minus delta over delta x1 and then f. So let us first write this f matrix now. In this case f equal to this fellow is a column vector, and the first one is just v out here, it's clear, and the second portion is minus gamma v minus 1 over m v prime of x. That is this column. And what is D? Or the matrix D equal to, well, it is the same as before, because you can see that this thing here is acting, oh, in this problem what is n equal to? 2, of course, and what is nu equal to? 1, that is trivially true. Only one of these equations has noise, the other one does not. So this is a very trivial case, but the reason I wrote this down is because I am now going to require you next to do this for the 3-dimensional case when you have an external field potential as well as a magnetic field, which will make a velocity dependent force. So that is a little intricate, but it is a 6-dimensional phase space, but we can write the equations down given the general expressions. Now what is this matrix equal to? It is obviously equal to 0, 0, 0 and half the square of this, which is gamma k Boltzmann T over m. this case. And now we are all set. All we got to do is to copy this and write the equation down for rho. So this says therefore rho of x bt satisfies the Fokker-Planck equation delta rho over delta t equal to minus, there is a minus here, and then the v comes out because the first is delta over delta x times v rho, but v is independent of x as before. So this term is still present, minus v delta rho over delta x. This is the convective derivative v dot del with respect to the coordinate. And then there is another term here, and what is that? That is equal to plus gamma delta over delta v, v rho, that is this portion, takes care of this, and then there is a plus 1 over m delta over delta v of v prime of x times rho, but v is independent of x. So, v prime of x comes out, that term sits there, and then finally there is only one diffusion term here, which is plus gamma k Boltzmann T over m d2 rho over dx dv2. So that is the equation for the phase space density, the one particle phase space density in the presence of an external potential V of x for a Brownian particle. That is the exact equation. Right? There is no guarantee that the solution to this is a Gaussian, a joint Gaussian in x and v, because this term is a mess. This term is a mess. No guarantee at all. In general, it is some complicated nonlinear function of x, and there is no guarantee of anything here. This equation is called the Kramer's equation. Generalized to other potentials in 3 dimensions, maybe even velocity dependent forces, we do not care. So, some generalization of this is the Kramer's equation. This is the simplest form of the Kramer's equation. Now, of course, you can recognize the oscillator case very trivially, because the oscillator case goes back to the old problem. So, if oscillator case potential implies that this term is, this is m omega naught squared x. So, this term becomes omega naught squared delta rho over delta, omega naught squared x delta rho by delta v. This particular term. It is a linear term. So, it could in fact be combined with all these fellows here. It reduces to the old case, which has already been solved, but this is a little harder to solve in this case, because while the diffusion matrix remains the same, this will imply that this matrix K that we had written down, which was 0, minus 1, 0, gamma, in the free particle case, what would it be in this case? Remember, there is an extra force here. This is minus omega naught squared x. So, if we bring it to the left, it is omega naught squared x, x not v, right. So, the drift would have one more term. This is still 0, x dot is minus v, but there is a term here, it is omega naught squared in this problem, and the d would look exactly the same as before. This is not so simple to exponentiate, although it is any 2 by 2 matrix can be exponentiated. Why do I say that? Because with the 0 here, the eigenvalues are 0 and gamma, and exponentiating this matrix would have been trivial, because k squared would have been proportional to gamma k or something like that. But now that is not going to happen. There are two eigenvalues here which depend on both gamma and omega naught squared. Not surprisingly, they would be precisely the eigenvalues of the zeros of the susceptibility, the poles of the susceptibility. So, they depend on whether they are underdamped, overdamped, critically damped, etc. Definitely have that. So, the solution will be in terms of trigonometric functions and a damped exponential in the underdamped case, or hyperbolic functions in the overdamped case, etc. So, it is considerably more messy, although you can exponentiate this, it is not hard, but this is where it would change. But we can write the formal equation down here. Now, what do you expect the solution of such an equation to become for long times? I would still like to look at the diffusion regime and see what happens. In the free particle case, when this was not there, recall that this rho asymptotically went to a product of the equilibrium Maxwellian distribution in V multiplied by the solution of the free diffusion equation in X, right. Now, what do you think will happen? Will that happen in this problem as well? Well, in general, you have to look at what happens when T is much bigger than gamma inverse, the diffusion regime, or gamma is very large, the high friction limit. So, you have to ask what happens to the solution in that high friction limit. But there is also a length scale in the problem. So, now the diffusion regime is defined as follows: diffusion not only should you have T much greater than gamma inverse, but also the force V prime of x must not vary too rapidly within the characteristic length scale. So, it is as if the force did not exist at all in that length scale, right, or a constant or whatever. So, within V squared equilibrium to the half divided by gamma. So, that will give you a criterion. You can compute this number and then check whether V prime or the force is rapidly varying spatially or not. If it is a gentle potential of some kind, it would not vary significantly. Then how would you go to this regime? What would you do? You do exactly what you did for the original free particle case. Namely, you would say, I am going to throw away the inertia term, look at the high friction limit and ask what happens there, right. So, in that high friction limit, let us write it down below this. So, what happens is that this rho tends in the diffusion regime to P equilibrium of V multiplied by an equation for P of x comma t where P of x comma t satisfies the Fokker-Planck equation corresponding to setting the friction term, setting the inertia term to 0. Right. So, essentially what you are doing is to take mx double dot plus m gamma x dot, right, equal to minus V prime of x plus a noise, and the noise was precisely the noise that we had in the original. So, 2 m gamma k Boltzmann T times zeta of T, this term, and you are dropping this term, the high friction limit. So, this term dominates, right. So, that gives us an equation which says x dot equal to minus 1 over m gamma V prime of x, that is the drift term, plus square root of, I have to divide by m squared gamma squared. So, it is twice k Boltzmann T over m gamma, that is our old friend square root of 2d appearing again times zeta of t. Corresponding to this stochastic equation, right. And what is this stochastic equation? Corresponding to x dot equal to minus 1 over m gamma v prime of x plus square root of 2 k Boltzmann T over m gamma zeta of t. That is a one dimensional equation with a nonlinear drift down here, but we know how to write the Fokker-Planck equation down for it. So, what would that be? In other words, delta over delta t of p of x comma t should be equal to, with a minus sign, so that goes away, and then you have equal to 1 over m gamma sitting here, d over dx now of v prime of x times p, because that is inside, you can't do anything about it, right, plus the second derivative half of the square of this, which is kt over m gamma, but that is just our old friend d, plus d times d2p over dx2. This is as before k Boltzmann T over m. That is the Fokker-Planck equation. This equation is called the Smoluchowski equation. So, it gives you the diffusion equation in the presence of a potential. But you see where it comes from, it really comes from the Fokker-Planck equation in phase space. It gets reduced to this in the diffusion regime, where you have to have an extra criterion now about the variation of v prime of x. We have not taken, we have not done the problem in the presence of a velocity dependent force. I assume that the external force was a potential which depends only on the position. So, no velocity dependent forces, no magnetic field, etc. has been included here as yet. Now, the question is, does this have any equilibrium solution or not as t tends to infinity? We know that if it is not, this is not there, it does not, it is just the Gaussian which tends to 0, flattens out. But now this will depend on what this v prime of x is. We kind of expect that if you had a confining potential that prevents you from having long range diffusion, then the mean square displacement will not diverge with t, and therefore there might be an equilibrium case. For instance, the oscillator. Now, let us look at the harmonic oscillator in the overdamped, highly overdamped, high friction limit case. So, highly overdamped what is the Smoluchowski equation for the position probability density of the highly overdamped harmonic oscillator? Well, this fellow is trivial to write down, it is m omega naught squared x, and the m cancels, right. So, you end up with delta p over delta t equal to omega naught squared over gamma times delta over delta x of xp plus d times, this is kt over m gamma that is the Fokker-Planck equation. Does it remind you of any other Fokker-Planck equation you have seen? Yeah, the velocity process for a free particle. What did that equation look like? That looked like delta p over delta t equal to gamma delta over delta v times v times p plus gamma k Boltzmann T over m d2p over dx2 dv2, where this p was p of v comma t, whereas this p is p of x comma t. It is not the same function, of course. Aren't these identical? Apart from a reinterpretation of constants. The 1 over the gamma here is replaced by omega naught squared by gamma, and same physical dimensions for both, and the kt over m gamma is replaced by gamma kt over m. This is the diffusion constant in velocity space for a free particle, or for a particle in the presence of a potential, it does not matter. That is the diffusion constant in position space. What was the solution to this equation? The Ornstein-Uhlenbeck distribution with a mean which went like e to the v naught e to the minus gamma t, and a variance which started with the delta function with 0 and then went to the variance of the equilibrium Maxwellian. So, there was an equilibrium distribution which was precisely the Maxwellian distribution. This is exactly the same, mathematically exactly the same problem. So, that is why you would very often see the Ornstein-Uhlenbeck process described in some books as the oscillator process. What they mean is that the conditional density of the simple harmonic oscillator, a harmonically bound particle, the Fokker-Planck equation satisfying that gives you the Ornstein-Uhlenbeck distribution, just as for the free particle the velocity has this Ornstein-Uhlenbeck distribution. In the overdamped limit, in the Smoluchowski approximation, this thing becomes precisely the Ornstein-Uhlenbeck distribution. Okay. Now, how do you find the equilibrium distribution in this case? You would set this to equal to 0, then you would find the current here would vanish at infinity, you would get the Gaussian e to the minus m v naught squared over 2 kt. What will you get here? What would be that distribution? So, there is an equilibrium distribution in this case. We have to look at the general case, we will subsequently, or when you have an equilibrium distribution, but in this case there is no doubt at all that p of x t tends as t tends to infinity. There is genuinely an equilibrium distribution here, because that would correspond to setting this equal to 0, then this is d over dx comes out and you becomes whatever is inside is a constant which can be set equal to 0 for normalizable distribution, and then you get dp over dx plus omega squared over gamma times m gamma over kt times p equal to 0. So, what would you get? And there is an x. So, what kind of solution do you get? It is a Gaussian, and what would that Gaussian be? Constant times e to the power minus, pardon me, s m omega naught squared x squared over twice k Boltzmann t. Right? You expect that, of course, because that is the Boltzmann factor for the potential energy of oscillator. In equilibrium, you expect it to go to the Gibbs distribution, the Maxwell-Boltzmann distribution. So, it is e to the minus the Hamiltonian, and the Hamiltonian is half mv squared plus half m omega naught squared x squared divided by kt, which is what is coming out. So, you want that as a consistency check, otherwise you are really off, right. So, you do expect that this will go to the Maxwellian, the Gaussian distribution. In the general case, no guarantee as yet, because you would have to set this equal to 0 and then ask whether this ordinary differential equation has a solution or not. Okay. And yes, suppose it has a solution, what would that look like? So, this becomes a dx, d over dx, p equilibrium, this becomes d2p over dx2 equilibrium. What would this solution look like? we want this to be equal to 0. Now of course that simply means d over dx of this whole business, the current could be constant, it could be going to some stationary constant current. Then without knowledge of that stationary current you can't solve the problem. But let us assume that at t equal at plus minus infinity this thing vanishes. Then what you have is an ordinary differential equation which says d dp equilibrium over dx plus 1 over m gamma times v prime of x p equilibrium equal to 0. But d is kT over m gamma. There can't be any reference to the friction constant in the equilibrium positional distribution, right. So this goes away and this was a kT, so this becomes k Boltzmann T, and what would that tell you? Yeah, this tells you, implies P equilibrium of x is proportional to e to the power minus v of x over k Boltzmann. The integral of v prime x is v of x, but that is just the Boltzmann factor, which is what you expect in equilibrium, that it will be e to the minus the Hamiltonian over kT, and the Hamiltonian has a kinetic part which you took care of separately, and then a potential which is precisely this. Okay. So it checks, this thing checks. There are other possibilities, we have assumed the stationary current is not there, but otherwise. So this will happen whenever this v of x is bounded. I mean it binds the part, sort of stops long range diffusion, then the particle is bound in some sense and it cannot diffuse out to infinity, and you end up with an equilibrium stationary distribution. Okay. No guarantee that it always exists, but in these cases, in normal cases it would exist. Okay. So the magnetic field case is a little more intricate than this, and we will talk about this later on and then see how to generalize this. Okay, let's stop this.